Hello, I'm Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This lesson is going to be on conservation of energy, and it's tied to the course Intermediate Thermodynamics. Our goal for this lesson is that by the end of the lesson, you should be reminded of the most common forms of the energy balance. Now, we will not be looking at example problems in this video. In the last lesson, we looked at the conservation equation. And we said that for some quantity x, we could do a general balance. In this case, we're going to apply this to energy. Inside the system, this x is the total energy in the system, which is the combination of internal energy, kinetic energy, and potential energy. The energy that crosses the boundaries will be the form Q and W. Now, for Q, heat transfer, we assign the sign to be positive for energy transferred into the system and negative for energy outside of the system, so energy loss. For W in this course, we will be using the same sign convention. Now, this is not universal. For Q, the sign convention is universal. For W, it is not. So if you look at some of my other video lessons, you will see that I do not use this sign convention in other courses. This sign convention is the chemical sign convention. The other is considered generally the mechanical sign convention. So whenever you're looking at anything related to the first law, be sure that you are using the correct sign convention for your Q and for your W in particular. Now, in addition to the Q and W crossing the boundary, you may have some mass that crosses the boundary, and that mass is going to require some work to move across the boundary. This work is going to be PV times the incremental mass moved over the boundary during the time period. We do not have energy generation, however, and so this simplifies to this form here. So here we have the energy change over a period of time in the system, the amount that is carried across, and the amount of energy it takes to move that across the borders. And then we have heat transfer, shaft work, and any work of moving the molecules within the volume. So maybe the boundaries are stretching, and so that movement equivalent to the PV work of moving mass across the boundary, it can be going on inside. Now we typically define H to be the enthalpy, and it is U plus PV. And it's just another property of our materials that we can look up. If we use W instead of W sub S, we're going to indicate that we are combining the shaft work with expansion work. Expansion work is this change of volume and the work required to move the molecules into this new space. Now, if you do this, the W and the PdV are going to combine into just W down here. And this U with the PV for the movement across the boundary is going to combine to H right here, and we get the simplified form of the general energy balance. And this is an equation that I think most people have seen a few times. Typically, though, when we look at this, the derivative is distressing for sometimes to work with, and so often we integrate this with respect to time. Now, if we do this, integrating with respect to time from time t1 to time t2, then we end up with this form. So we just have the change of what happened inside from the final time minus the beginning time. We often designate that with a delta instead of showing the subtraction of state 2 minus state 1. And then the sum of the integrals of everything that came across the boundaries plus the total Q and the total W. The only visible difference between this and the previous on Q and W is that they lost the dot, but that means that it's integrated over time. It's the rate integrated over time, so it's the total amount of heat transfer that occurred, the total amount of work that occurred. We have two favorite specializations of the mass balance, or excuse me, energy balance. And in this particular case, we're going to look at a closed system. When the system is closed, it means that no mass is entering or exiting. And so we get rid of that group that had the summation in front of it for the mass entering and exiting. And we end up with just the change in internal energy, kinetic, and potential energy for the system at state 2 minus state 1. And this is going to equal to the amount of heat transfer and the amount of work that cross the boundaries. For a steady state system, there won't be any change over time. And so in this case, we get rid of the part that had the ddt. Now this is again going before we integrated with time. But if I get rid of the ddt, because no change with time, there's no reason to integrate with time. And so I end up with this as my simplified energy balance. And this is great, but it is a little confusing and probably not the form you're most accustomed to seeing. A lot of times we will just simply rearrange these so that we isolate the Q and W on one side. And then here we are going to separate out for all of the various ways that mass can cross in or out. Let's just look at it as a stream entering or exiting. And if we do this, the signs end up taking care of themselves as Q plus W equals the sum of all of the exiting energy minus the sum of all of the inlet energy. And again, because it was flow, it has this H plus P or U plus PV, which combines as H. So this completes this video lesson. We will be looking at examples in future lessons. We also are going to be talking about how to find the data. If you need a more in-depth review, there are some other video reviews at a more basic level that you may wish to view. Thank you.